Hello guys, hope everyone is doing good. Welcome to a new session on engineering graphics. In this session, we will be learning about orthographic projections. Now, what is this orthographic projection? If you go by definition, if you take a simple definition, now it is the projection of the view of an object onto a 2D surface. Okay, that is, you project the view of a particular object onto a 2D surface, and the lines of projection are actually perpendicular to that 2D surface. So the lines of projection will be perpendicular to that 2D surface. That is the most important part. So orthographic projection actually deals with perpendicular lines. Okay, it is a projection that actually deals with perpendicular lines. Now in engineering graphics there are other different types of projections also, like you have isometric projections, you have perspective projections, and so on. Okay, but right now our aim is to focus mainly on the orthographic projection. And as far as engineering graphics for BTech students and everyone is concerned, orthographic projections, it covers a lot of portion of the total syllabus. So today, with the help of some animations and some realistic examples, with the help of some lights and shadows and some realistic examples and some animations, I'll give you an introduction on orthographic projection. So I hope that you got the name orthographic projection, you got the idea what this orthographic projection is. So we will now move on to the visualization and the explanations. Okay, so here I'm going to explain orthographic projection with the help of some realistic examples. You can see three colors here, right? Three rectangles or square or something like that. Three small squares which is not actually kept perpendicular. Now let us assume that these are three walls of a room. Okay, there is a vertical wall, pink vertical wall, a green vertical wall, and an yellow floor. Okay, let us assume that this to be the walls of a room, and these are, when it is, as you know, the walls of a room are actually mutually perpendicular to each other, right? Now these are also mutually perpendicular to each other. It doesn't seem so, but let us just rotate it and see. Then we will understand that this is mutually perpendicular to each other. Okay, so yeah, see that it is actually perpendicular to each other. Okay, now the reason why I brought in this thing is to explain how are we going to draw this orthographic projection. Okay, so what I'm going to do here is I'm going to keep an object in between this and then switch on the lights. Then let us see how the shadow is forming. We'll just see how the shadow is forming. We'll first keep an object there, then switch on the lights and see how the shadow will form. Okay, so I'm just going to keep an object there. Now I've kept the object there. Now this is a cuboid. Okay, or in graphics terms it is a rectangular prism. Okay, as you can see here, there is a height, then you have a width, and you have a thickness. A height is there, your width is there, and there is a thickness. Now what I'm going to do is I'm going to switch on the lights in the room. Okay, so if I switch on the lights in the room, see that, yeah, now I have switched on all the three lights in the room. Now see what has happened. There is a light coming from here, there is a light coming from the top, and there's a light coming from the right. Light from the left, light from the top, and light from the right. Now if you look at the light from the left, it is falling on this surface. It's falling on this surface, and it casts a shadow behind that on the wall, right? Similarly, if you look at the light coming from the right, it will cast a shadow on the wall. And you can see that that shadow has the same shape as of this face, and the previous shadow had the same shape as this one, this face. And the light coming from the top, that will also form a shadow there. Okay, and the shadow has this shape. Now if you observe natural light in natural world, if you just observe natural light, what happens if we move this object towards a wall or towards a light? If you move towards a light, you can see that the size of this shadow will increase, and if you move towards the wall, the size of the shadow will actually decrease, right? Finally it will become the same size as that of the object. Why is that? It is because of the diverging nature of light. Okay, usually if you switch on a torch, you can see that light is actually diverging. The the light from the torch will actually diverge. Okay, now due to that effect, the shadow will increase and decrease. It will grow and it will also decrease. Okay, but now we are learning orthographic projection. We are not learning about natural light. Now the peculiarity of orthographic projection is that, from the definition, when we heard the definition before, the orthographic projection deals with perpendicular lines. Okay, orthographic projection deals with perpendicular lines, and the line should be perpendicular to the 2D surface. Now this is a 2D surface, right? This is a 2D surface. This is the object, and this, the light falls on this one, and you're making the projection of this particular view and onto a 2D surface, and the lines of projection will be perpendicular to those surfaces. The lines should be perpendicular. Now for natural light, if you start from here, the light will fall on one corner and it will actually diverge. So naturally the shadow should be larger than the object, but here the shadow is same as that of the object. The reason is that we are using perpendicular lines. This light source is kind of a laser light source. Now what is the peculiarity about laser beams? The laser beams are actually parallel to each other. They don't have a diverging nature or a converging nature. Since they don't have a diverging nature, it will be parallel to these lines. When it is parallel, it finally go and hit the surface and it will be perpendicular to that surface. So the projection lines from this object to the shadow will be perpendicular. So that is why this kind of projection is called orthographic projection. Okay, on this surface also it is the same, and on this surface also it's the same, right? I hope you got an idea. But the problem with this kind of a figure is that this is a wall, right? These are three mutually perpendicular walls, and you can't make a drawing out of this. So for our convenience, what we do is we make these drawings on a quadrant system. Okay, so it is easier to make these drawings on a quadrant system, just like we have quadrant system for mathematics, right? For mathematics, in mathematics we have quadrant system. Why do we need the quadrant system? Quadrant system actually, it works as a reference. In this case also, the quadrant system in engineering graphics also works as a reference. Let us see how it works as a reference. So you have a height from the bottom, from the floor. You have a distance from the this vertical wall, and you have another distance from this vertical wall. So if you have a quadrant system, we can say, okay, 10 meters from the horizontal line, 20 meter or 10 meters from the x axis, 20 meters from the y axis, etc. So let us see what is the quadrant system in graphics. Okay, so I'm just switching off the light. See, when I switched off the light, so shadow is gone. I took away the object. Now I'm just, instead of using this, I'm going to use a quadrant system. Now if you look at this figure, you can see a quadrant system now, just like engineering math or mathematics, sorry, we can see a quadrant system wherein you have first quadrant, second quadrant, third quadrant, and fourth quadrant. Now, as far as graphics is concerned, there are so many properties for this quadrant system. Different you get different figures and different methods of projection in all different quadrant systems. We'll come to all those things later on. Now we are not going to discuss that. We'll come to the properties of different quadrant systems and everything. Right now, I'll just give you an example, a simple introduction on how this orthographic projection is done on a quadrant system. Now, the pink wall, okay, or the pink plane in engineering graphics, the quadrant system, it is called as a vertical plane, and of course the yellow plane is called as a horizontal plane. Okay, for every quadrant, first quadrant, second quadrant, third quadrant, and fourth quadrant, there is a horizontal plane and there is a vertical plane. Just like we saw the vertical wall and horizontal wall. What we are doing here is we are going to place an object somewhere here, and then we will use the same source of light and project it onto the surface. So we have a reference. Now this horizontal plane acts as a reference and also acts as a screen on which the shadow is falling. Similarly, the vertical plane also acts as a reference and it acts as a screen also. Now let us see, let us bring in an object. So this is the side view. Yeah, now we have the object. I've switched on the lights. Now when I switch on the light, you can see that the shadow is falling on this one. So the front view, this is FV is given here, that is the front view. TV is given here, that is a top view. So light comes from the top and light comes from the left side. The left side is the front view. Assume that you're looking from the front. So when light comes from the left side, the shadow of this ball is falling on this. When light comes from the top, the shadow is falling on the horizontal plane. Now when I switch off the light or when I take away the object, the shadows will move away. So what I'll do is we'll just make two markings here. Okay, so we'll make two markings there. Yeah, we have the two markings there. And then what is this purple line and the green line? You see, this purple line represents the distance of the object from the vertical plane. Okay, you see that? Distance of the object from the vertical plane. Similar to this, the green line represents the distance of the object from the horizontal plane. Now the shadow, you see the shadow, since there is a light from the top, there is a shadow for this purple line that is coming here, and the shadow for the green line that is coming here. You can see that these two are mutually perpendicular too. Okay, and this mutual, the reason why I highlighted that it is mutually perpendicular is yeah, we'll see that later on. Now this purple line and this shadow should be of the same length, right? So this shadow also represents the distance from the vertical plane. Similarly, this green line and its shadow has the same length. Now actually the green line is the distance from the horizontal plane, so this should also be the distance from the horizontal plane. So those things are actually marked there. See that the distance from the vertical plane and distance from the horizontal plane. Now we will see, now this is not a, like we are not looking from the front directly, so we'll just rotate this quadrant and look from the front directly and see what happens. Okay, before that I'll remove the ball. Now I can remove the ball and these lines because we already have the shadows there. Okay, the shadow of the object is here, the front view. This is the front view, this is the top view, and these are the distance from VP and distance from HP. So I'll remove the object and switch off the lights. Okay, now I'm turning the quadrant system towards and I'm directly looking at the quadrant system, directly looking at the vertical plane. Okay, and that is the front view. And let us see, when this horizontal plane comes to our eye level, what happens? When this horizontal plane comes to our eye level, what happens? Yeah, see what has happened? Just went away. What happened there? This horizontal plane has become a line. So yeah, see that when the horizontal plane has reach the eye level, when I'm looking from the front, now see this is the front view, when I'm looking from the front, the plane has become a line. Now this line, which is represented by xy in a drawing, in a graphical engineering graphical drawing, is actually the HP itself, right? It's the HP in the front view. When you look from the front, this is all you see. This small line is all you see of HP, right? Instead of HP, you see the small line. You don't see the plane there. That's all you see. You see only the line. Let us see what you see in the top view. When you look from the top, yeah, similar to that. See that? Now the pink plane itself is gone. The vertical plane itself is gone. All you see is a line. So this line is actually right now the projection. It is the projection of the top view onto the horizontal plane, and the other one was the projection of the front view onto the horizontal plane. Now our aim is, we'll go back, and now our aim is to open this quadrant system. Now how do you open the quadrant system? As you can see, this is slowly opening up. When you open the quadrant system, when you open the first quadrant, you see the horizontal plane is moving down in the first quadrant. At the same time, the horizontal plane is moving up in the second quadrant. Okay, it is moving down in the first quadrant and it is moving up in the second quadrant. Now you see the front view is actually moving down, and you see this line, the joining line, intersection line of the horizontal plane and the vertical plane. Remember, I told you that this is the front view of the horizontal plane and top view of the vertical plane. Both these will be there, right? So let us see what happens. Yeah, now this 3D quadrant system has become a 2D plane. Okay, so if I look at from the front, you can see the 3D quadrant system has become a 2D plane. Okay, and the front view is here and the top view is here. The front view, which is the green one, is here, and this is the red dot is the top view, and that is projected onto the horizontal plane and it is gone down. And this line of intersection is the projection of the horizontal plane in the front view and the projection of the vertical plane in the top view. Okay, so this is the final drawing. Now you have a 2D plane, right? 2D. This is actually converted into a 2D plane. The drawing is actually converted into the 2D plane. You have the front view and you have the top view on this 2D plane. Now you have, if it is required, we can also have a side view, but since this is a sphere, actually we do not want the side view. Similar to this thing, you can just open up the side view and you can see when in the case of solids, complicated figures and all those things, we will need a side view and we will see how that side view looks like. Okay, now what we will do is, I'll just show you another figure, an actual drawing of this engineering graphics, actual two-dimensional drawing. Okay, this is the idea behind that, and I'll just show you the actual drawing. How do you draw that? Okay, now we will move on to that one. Okay, yeah, we will move on to that thing. Okay, so here we have a actual two-dimensional drawing, okay, of the symbol of a symbol figure, or of a symbol object. Okay, two-dimensional graphical drawing of a two-dimensional object. This is the orthographic projection of a small ball. Okay, and I have named the ball as A. As you have seen in the animation, you have the front view above the XY line. You saw the VP there and HP there. All those things were there, exactly the same as the animation. And the distance from HP is marked here. Okay, this is the distance from HP, and this is how you give the dimensions. And the front view is marked as A prime, and you have the front view of the ball. The shadow of the ball is here, and this is the top view. The top view is here, and it is named as A, and this is the distance from VP. Okay, this is just a simple drawing, and then now we will, in the subsequent classes, in the when we move forward, we will move on to complicated drawings and drawings with more dimensions, 2D drawings and 3D drawings and all those things. And then we will see more complicated shapes. How do you rotate those? We'll use projection of lines, projection of solids, projection of planes, etc., etc. And all these things will have animations also. Okay, so until we see you next time, take care and be safe. Thank you.